reading chapter 10. Chapter 10 is actually, I think, really fun and different, but doable. 10.1 you'll probably like. 10.1 and 10.2 most people do pretty well with. When you get to 10.3, that's when all the trig comes in everywhere. So if you haven't brushed up on your trig, you want to do it before we get to 10.3. So today we're doing 10.1 and half of 10.2. And then when I see you on Thursday, we're doing the rest of 10.2 and all of 10.3. And then we're going away for a week. We're going to do something fun.
When's your test?
Not till like a week after spring break.
That's not very fun.
But you have spring break to review if you're not going off to do something fun. Which you should. So 10.1 and 10.3 are not due until after, 10.1 through 10.3 are not due until after spring break.
Yeah. Hey, that makes sense.
But here's the other piece of small bad news. For those of you who like to email me and ask me questions, I won't be online over spring break. So you should probably get on it sooner than later, and that way you don't have to worry about it because I won't be able to answer your questions. I'm going to have a break too, just so you know. I'll remind you that we're going to camp this semester. Okay, comments, questions? We're good? Wait. Page 91? Okay, we ready? We think? 10.1, curves defined by parametric equations. So it's another way to write equations for different curves, like we've done, parabolas, and we actually know the equation for a circle. Like what's the equation for a circle with radius r if it's centered at the origin? X squared plus y squared equals r squared. We've seen that before. A picture of it. Pretend that's a circle where the radius is r. Is this a function? No, because it doesn't pass the vertical line test. Y is not a function of x. X is not a function of y. A lot of times you have curves that are not functions. And you learned back in algebra that you could make this into two separate functions. Like the top half is the positive square root if you solved for y. It's maybe the plus or minus like you guys were talking about on today's quiz. Something similar to this. You could make it two different pieces and graph the top half and graph the bottom half and it would make the circle. But what we're going to do now is talk about parametric equations, which gives us a way to do all kinds of interesting curves that maybe aren't functions, maybe they curve back over themselves, but we can still define them with equations. And maybe your curve does something like this. Who knows? And we'll be able to define those. Definitely not a function. Okay? So what it means when they call them parametric is there's a third variable which they call their parameter. I like to think of it as time. Imagine if I was drawing this circle. Start over. Say I'm drawing that circle and I start over here at the radius r, and I want to draw it going clockwise. As time goes by, like after 1 second I might be up here, and after 2 seconds I might be here, and after 3 seconds, 4 seconds, 5, 6, 7. So maybe it takes me 8 seconds to draw that. So with time I was actually plotting a bunch of points. So at 1 second and at half, so here's where I said I was at 1 second, but maybe here's where I was at half a second, and then a quarter of a second. So I was filling in all these dots at all those moments in time. And I actually was going in this direction as I drew it. So the parametric equation, if you think of it with time, it's plotting points with time and then connecting those dots. And there will always be a direction. This curve is different than this curve when I draw it counterclockwise. Because the point, well, not the curve itself. The curve when you look at it is still the same circle, but the direction changes. So here, after 1 second, I was probably down here in the fourth quadrant, and then I was here. So the points are different at certain times. They do give you the same shape, but the parameter tells you the direction as well. So you'll be asked to draw things, sketch the curve, including the direction. All right, so that's kind of an overview of what parameters do. So it's a little blurb there on your notes about you can't write y as a function of x, and you can't write x is a function of y. It just doesn't work. Like with this, you can't just solve for x there or just solve for y without that plus or minus. So that's where we introduce this third variable, which is our parameter. We call this a parametric curve. It's a curve and the parameter gives you that direction, it shows you which way you're drawing it. So we're going to jump in with example 1 to kind of make some sense of this. So example 1 says, what curve is represented by x equals cosine t, y equals sine t, and t has to be between 0 and 2 pi. So they want to know what curve is represented by this. So you still have your x's and your y's, which are the points that you're going to plot. But here's your third variable, this t. That's like, I always think of it as time. As at 1 second, where am I? At 2 seconds, where am I? And so forth. It doesn't have to be time, but it makes more sense. So the question is, what is that going to look like? Some of you may already know. Don't tell me if you do. The idea is I'm just going to plot some points. I'm just going to plot some points. In the old days, we just made x, y pairs, right? We plotted points. But because I have this other parameter of t, I have to include that as well. So let's just start with t equals 0. When t equals 0, I want to know what x and y go with those values of that value of t. So cosine of 0 is 1, and sine of 0 is 0. So these ones right here, that's like an xy pair. 1, 0 is a point on my curve. So that tells me that, I'll put 1 right here. At time 0, I'm starting right here at this point, 1, 0. Now I'm going to pick values of t that are nicer to plug in here than 1s, 2s, 3s, and so forth, because if you ask me the cosine of 2, I don't really know what that is. So I'm going to pick, some radians. Maybe I'll pick pi over 6. Just another value of t higher than this one. So here's where we're doing some trig already. Cosine of pi over 6, that's 30 degrees.
3 over.
Yeah, root 3 over 2. And the sine of that, 1 half. Again, you don't have to put parentheses. I like to put them there so you can recognize it as an ordered pair. Root 3 over 2 is around, let's see, it's like 0.8-ish. Can someone do that in their calculator?
0.66.
0.66?
0.86.
0.86. So this is roughly 0.86 and 1 half. So if I wanted to plot this point, 0.86 is maybe over here, right? And up, let me put a 1 up here. 0.86 and up 1 half, so maybe I'm right here. What I did is I just turned that into a decimal so I could find it on the graph. Guess which one I'm going to pick next for t? Pi over 4? Yeah, I'm just going to keep going and do pi's that I know. Pi over 4, both the cosine and the sine are root 2 over 2 in that case, which are around 0.7-ish, 0.7. So if I come over here, approximately 0.7 and up 0.7, I may be here. Just plotting points. I'm turning those into decimals as I do it, because I can't find them either by looking at them that way. We all right with getting those points? How about pi over 3? Yeah, just the opposite of these guys, right? 1 half root 3 over 2. So now I'm going over 1 half and up root 3 over 2, I may be here. And then the next one I'm going to do is pi over 2. 0 and 1. So I'm up here. So if I just connect those values there for the t's from 0 to pi over 2, I end up getting this little shape here with this direction, right? Because that's the direction as t increased, that's the direction the curve was going. The direction always goes, if t is increasing, which way does it go? What do you think that is, my beautiful artwork?
Fourth mission.
A quarter of a circle. Partly because if you think about sines and cosines, they go with what's called the unit circle, where the radius is 1. So what do you think would happen if I went from pi over 2 to pi? Yeah, I would probably get this other part right here. And then from pi to 3 pi over 2, I would get this, and then I'd end up back over here. You could plot more points if you would like. But basically, from 0 to 2 pi, you're getting all of those points in the whole 4 quadrants on the unit circle. That's the definition of the unit circle way back when. So I defined this circle with these parametric equations. What would the equation of this circle have been in this form? What would it have looked like if I written it that way?
Sine squared of t plus cosine squared of t is equal.
You're a step ahead of me. I'm going to get there. But if I had just said, what's the equation of that circle? If you didn't know anything about parameters or where it came from, what's the radius of that circle? 1. So it would have been x squared plus y squared equals 1 squared. But I'm going to take what Chad said because he's exactly going where I wanted to go. We already know the equation of that circle, because the radius is 1, is this. Well, imagine if we take these parameters. X is cosine, so cosine squared. Y is sine, show you sine squared. Oops. Those are t's, not x's. Hang on. That's x squared plus y squared equals 1. What is this? Recognize that? It's the Pythagorean identity, right? So we already knew this was true. So a lot of times when you have things that are circular shaped, especially even if they're kind of roundish, you're going to have sines and cosines, and you're going to be using this Pythagorean identity to find this equation. This one was a circle, so we could just look at it. They're not all going to be circles. See that relationship between x and y, knowing their identity? So this defines that circle, and this defines that circle. Either way, I get the same shape. Questions? Kind of new, kind of weird. My next one's just changed a little bit. My next one, part of example 1, it says, what if we put a 4 in front of that cosine and a 9 in front of that sine? And don't change anything else. What's going to happen to all the x's if I put a 4 in front of them? They're all going to get bigger, but multiplied by a factor of 4, right? So essentially, every one of these is going to be multiplied by 4. And every one of these is going to be multiplied by 9. That's all it's going to change, right? I'm going to make that table. Oops. X, Y. 0, pi over 6, pi over 4. Just recopying the same parameters. Parameters of that t variable. I'm just taking each one of those x values and multiplying them by 4. So this will be 4. That'll be 2 square root of 3. That'll be 2 square root of 2. That'll be a 2 and a 0. I'm taking all of these numbers here and multiplying them by 4. And then I'm going to take all of those and multiply them by 9. 0, 9 over 2, 9 root 2 over 2. I'm going to need someone with a calculator to help me graph these in a minute. 9 root 3 over 2 and 9. You're totally right. So those are just multiplying all the original x's by 4 and all the y's by 9. So now I'm going to try to draw this. I'm starting at the point 4, 0. change my scale so I can fit it on here. I'm starting at 40. Where am I gonna end up at by the time I get to pi over 2? 0.9, so I need to go all the way up here to 9. So I'm starting here, just from this table, starting here and stopping there. And if we take these in between, someone have their calculator handy? What's 2√3 approximately? The decimal.
3.46.
So almost 3.5. This is 4.5. So 3.5. 2, 3, 4.5. 3.5, 4.5 is about here. How about this one, Jose? 2√2 times square root of 2? You're gonna be my calculator guy.
2.82.
2.8, and this one is 2.8 and
6.36.
6.3. So 2.8 and 6.3 is roughly here. How about here? I got the 2. I can do that one.
7.79.
7.79. So over 2, up 7.79 is roughly here, and then I end up over there. So you can see I'm still kind of curving up like this. Similar to my circle that I did, but it just now gets kind of stretched out. What do you think is going to happen if I continue? Same thing, right? I'll curve back down on this side, come over here to -4. I'll go all the way down here to -9. It's a horrible -9. It's supposed to be a -9. Pretend like it is. And then back up here to 4. So Chad said a minute ago, he said it's going to be an ellipse. Remember learning ellipses somewhere in your previous life before you met me? You should have learned it somewhere. Most people see it in pre-calc, some people see it in algebra and pre-calc. What's the equation for an ellipse? Anybody know?
Is that the one with an H after sine H, cosine H, or not?
It doesn't have H's in it necessarily. It's similar to the equation for a circle.
X minus like the radius.
It has an x minus the center, but the center in our case is 0. But in general, let me kind of write one over here. It looks something like this. X squared over a squared plus y squared over b squared equals 1. Should have seen that somewhere before. Look vaguely familiar now. Anyone know what a and b had to do with it? What did the a and b tell you about the graph?
Oh, is this the stretch factor?
Yeah, it's the stretch factor. It tells you how far out you go in the x and how far out you go in the y. So the a tells you how far it's like stretching that circle out, exactly. So let's hold that thought for a minute and figure out this equation. So I have these parameters here. I know this identity, right? I know this identity is always true. Let's squeeze it down underneath here. Can you solve this for cosine? Can you solve it for cosine? Cosine equals x over 4, right? X over 4. So cosine squared would be x over 4 squared. And if I solve this for sine, it'd be y over 9. So sine squared would be y over 9 squared equals 1. Just using the Pythagorean identity, that what we know about sines and cosines. If we simplify this, we get x squared over 16 plus y squared over 81 equals 1. This is the equation of an ellipse. And as Nick said, this is what we call like a stretch factor. You're going to go out, the square root of this is 4. 4 in the x direction and 9 in the y direction. Which is exactly what we had, right? We went out 4 in the x direction and 9 in the y direction. Those of you who don't like your trigger, it's everywhere. It's going to be all over chapter 10. This is nothing compared to the rest of chapter 10. Okay, let's look at one maybe that doesn't have trig. They don't all have trig. And on top of the next page, I talk about sometimes it's difficult to see what the curve will do. A lot of people can see what this is going to do just because they know the relationship between cosines and sines in the unit circle. So you can see it's going to be circular. But sometimes you have no clue what it's going to look like. So let's look at this next one here. My example 3. Which has x equals t squared plus t, y equals 2t minus 1, and we want to sketch this curve. So I need, again, some t's, some x's, and some y's. I'm not going to pick angles that are nice for sine anymore. I don't have to have zeros and pi's over 3's and pi over 6's. I just need to pick some t's, and I like to put them in here in increasing order because that will help me make sure I draw my curve in the right direction. So where do you want to start? -2? Okay. Let's do -2, and we'll increase our t's by 1, maybe this far. -2 to 2, we're just picking some t's in increasing order. We'll find out in a minute if that's a good starting point. I don't know yet, we're going to find out. So now for each of these t's, I'm going to plug them into these equations and find x and find y. I do this in my head, you guys all right with that? -2 squared, positive 4, plus -2, that's 4 minus 2, so that's 2. Did I skip an example? Do I have a different example than you?
Yeah, we don't have the spot, I need one.
Oh, I see, I gave you different values.
Yeah.
I'm with you. We'll change them. I like it. Thank you, Daniel, for catching that. So I already gave you some values, and he wants me to follow my notes, which is a good plan. I like that. Apparently I have to read them if I want to follow them. Now I'm reading them. I see what you're talking about. We're good now? Okay, but I plugged in -2 into here. Now I'm going to plug -2 into there. And I get -5. -4 minus 1. Somebody asked me a question. If you don't know where my numbers are coming from, I can show you the work. It's a little bit busy work. So now when I plug -1 into here, I get -1 squared, that's positive 1, plus -1, that's 0. And when I plug -1 into there, that's -3. Just completing some points here. -1/2, well that one's a little bit messy. Let's write that one down. That'll give me 1/4 plus -1/2. It's going to be -1/4. You lost the side maybe? -1/2. Right idea, you just lost the side, easy to do. -1/4, oh, it's nice when I plug it in over there. That gives me -2. Plugging my t's in. Zeros are easy. I get 0 and -1. And when I plug 1 in here, I get 2 here and 1. So we're doing some busy work, plugging in these values of t, which could have been the ones I originally wrote down, but I gave you them, sorry, so we're just plugging in those. So now we're going to plot those points in order. So the order matters. So I have to reach all the way to -5. So I'm starting at 2, -5. 2, -5, which is here. Then I'm at 0, -3, which is here. Then I'm at -1/4, -2. -1/4, -2 is about there. 0, -1. have to connect those in the order that I found them, because I have to connect them in the order of increasing t's. So I have to start here and connect them in this direction.
Would
Yes.
it be,
Wouldn't 200 on the axis?
yeah,
Oh, yeah, 2-1. It helps if I could graph too. Apparently my brain is on vacation already, it's not good. Sebastian and Carlos passed the test for being awake. The rest of you, I don't know. Including me. It's funny, because I was just looking at it going, man, that looks lopsided. Now I know why, I can't count. 1, 0, they're not the same. You think this is the whole graph? What's the rest of it gonna look like?
It loops back around.
What'd you say?
It'll loop back around.
You think it's gonna loop back around? How can we check to see if it loops back around?
plug in
Plug in some more points. Well, which one should we plug in?
You can plug in 0 and 1 or just kidding.
Just kidding.
I mean,
Yeah, what kind of t's would give us more information here?
3 and 4.
3 and 4? Remember when we were picking t's, we started at -2 and we went up to 1. So we either need to know what happens after this point or before this one, right? So let's start with after this one. This is my last point, this is when t equals 1. So if I want to know what happens after that, I'll just pick another t, maybe I'll pick t equals 2. Just to see what happens, because we're thinking it might loop back around. So if I plug 2 in here, now I get 4 plus 2, that's 6. 4 minus 1, that's 3. See if I can graph that correctly this time. 6, 3. 1, 2, 3, 4, 5, 6, and up 3. 1, 2, 3. It now does that. And if we want to know what happens before this, what might I pick for t? -3, a t that came before this one. Now, technically I like to put it up here, but I'm going to put it down here because I'm out of room. You can squeeze it in there. I think I'm going to squeeze in there anyhow. It'll make me happier. Watch me cheat a little bit. Power of the eraser. I'm going to squeeze this higher. That's not first. T comes first. I'm going to squeeze a -3 in there. They don't have to be in order, but I can visualize it better if they are. So this gives me +9 minus 3, so that's 6. -6 minus 1, -7. 6, -7. 5, 6, down 5, 6, 7, roughly here. Doesn't look like it's looping back around. What's it look like? Looks like a parabola. It is. It is a parabola. I'll warn you, a lot of you, when you learn to draw parabolas, I'll put another color so I can erase it. You would draw a parabola and then you'd put little arrows on the end, say it goes on forever, right? It technically goes on forever, but we can't put an arrow like this on this end. We have to put an arrow this way, right, because of the direction. It means it still is coming that way. A lot of times they'll put the arrow there, maybe even have this little piece going through it. And there's a parabola, it keeps going, but it's coming from that direction. This one turns out to be a parabola. Can't always tell by looking at them what they're going to be. Questions there? What if we had a restriction on here, which we sometimes are asked to graph? What if they said, okay, graph this curve, but here's a restriction. You only can do it for positive t's. If you only can have it for positive t's, how would that affect my graph?
You erase the graph from T0 and below.
Yeah, I would pretty much get rid of all this, right? And start here, right? Has to be greater than or equal to. So this point was 0, -1. So that means I would start here and only include this portion. And all the rest of it I would erase if I'd been given that restriction. So sometimes you're given restrictions. A lot of times t can only be positive because it actually does represent time, and we don't talk about what happened before we started something. If we start right now, t equals 0, and we don't talk about what happened last week. That's all old news. Go right there? Okay. So now the last thing is eliminating the variable. So you'll be asked to eliminate the parameter, which means get rid of your t. This is example 4. It means get rid of your t's. We were kind of doing that here, where we took this parametric curve and we wrote it in this form. There are no t's in this at all. And this is an equation that represents the circle. This is the equation that represents the circle. We did it over here. This defined our ellipse. And we said, oh, that's the equation of the ellipse. There are no t's in here. So a lot of times it helps to eliminate the parameter because then you get a shape that you recognize, you know how to graph it. So let's eliminate the parameter over here. It involves your fabulous algebra skills. One method is to solve for t and substitute. Eliminate parameter. This is example 4. It says eliminate the variable t. So I'm going to take these two equations and decide which one I like better in terms of solving for t. Pick one of them and solve for t. Which one would you rather solve for t? This one or this one?
Second.
Me too. I think I could solve for it here much easier. Can't solve that one. I could, but I have to complete the square. It'd be a mess. Everyone agree we could solve for t here? So if we do that, y equals 2t minus 1. So y plus 1 equals 2t. So t equals y plus 1 over 2. So I solved for t in that equation. I'm going to plug that t into this equation because both of them have to be the same, right? So now I'm going to substitute. I'm going to substitute, and it's going to say x equals that mess squared plus that. T squared plus t. Say you're lost. Did this make sense? No? Okay. This is the original equation for y here. I just took this and got the t by itself. Moved stuff around, isolated the t. Then I took that t and plugged it in here. And here. Now I have a mess that I'm going to simplify. Yes?
So you plug it into the other equation.
Yes, so you use one equation, you solve for t, and then you plug it into the other equation. So it's kind of like when you first learned systems of equations way back when in algebra, where you solved for one and plugged into the other one. It's very similar to that. You don't always have to do that method. Sometimes you use trig identities. Sometimes you look for similarities. I'll show you what the similarities in a little bit. But let's keep going with this one. So I want to simplify that. See if I simplified the whole thing nice and messy. So I'm going to say x equals, I'm going to have y plus 1 squared on top over 4. Right? Y plus 1 squared over 4 when I square this guy. Plus y plus 1 over 2. I'm just trying to simplify it and get it in terms of x, y, whatever I can to see what the heck it looks like. Notice the t's are already gone. There's no t's in there. Now we just want to kind of get it cleaner. Suggestions on how to clean that up.
Multiply it out and then do a common denominator.
Yeah, maybe multiply this out, and then maybe get a common denominator to put everything together. I like that plan. So if we multiply this out using FOIL, a distributive property, you'll get y squared plus 2y plus 1. And then we want to add it to this. Now to add these fractions, we need a common denominator. So we'll multiply this one by 2 over 2. So I have x equals y squared plus 2y plus 1 over 4 plus 2y plus 2 over 4. Now we could add them, hopefully. Y squared plus 4y plus 3 all over 4. Or if you want to make it look a little neater, you could maybe factor out that 1/4 and put the numerator in here. It doesn't really matter. Some people can see what it looks like here. So I have x equals a constant times this quadratic expression. Quadratics are always what when you graph them? Graph a parabola. Yeah, every time you graph a quadratic, it's a parabola. Now this one has x equals y squared, not y equals x squared. What does that tell us? It's going to be sideways, like your hand signal. It's either going to open to the left or the right, depending on if the sign is positive or negative. So it's positive and it's y squared, so it definitely opens to the right. Definitely opens to the right. So it's a parabola that opens to the right. What if I wanted to find like some intercepts? Like where it intersected the x-axis. Like say I wanted to find,
Find the zeros?
yeah. What if I wanted to find these points over here? Those points on the y-axis are when x equals 0?
So for what?
Yeah, solve for y. If I let x equal 0, if I let x equal 0, then I have 0 equals 1/4 times all that. Multiply through by 1/4, and that goes away. I'm gonna multiply through by 4, and that goes away. How are your factoring skills? Ooh, somebody's got good factoring skills. Y plus 3, y plus 1? Y equals -3 and negative what? What are those?
The y-intercepts.
Yeah, they're actually my x-intercepts,
X-intercepts.
because I let x equals 0, I did it, it's a sideways one. They're my x-intercepts. Oh no, sorry, they're the y-intercepts, I lied, you were totally right, Zach. They're where it hits my y-axis. I let x equals 0, those are my y-intercepts, at -1 and at -3. What if I wanted to find that point, which on my graph looks like 1, 1, but I don't know. What is this point right here? What if I want to find that one? Looks like 1, but you know you can't trust me. Yes, Evelyn?
Y equals 0?
Yeah, y equals 0 if you're on the x-axis. If you plug 0 in for y, let's look at it right here. If I plug 0 in for y, what will I get? 3 over 4. So my graph looks like it intersects at 1. It's actually at 3/4. So if I wanted to fix my graph a little bit, if this is 1, it actually crosses more like at 3/4, right there. That's pretty fine. So then you kind of help verify that your curve makes sense with the equations that you know, that you're familiar with. So the directions though are eliminate the parameter. This is your answer. X equals this, or x equals that, whichever way you want to write it. So when you're doing your homework online, sometimes it asks you to sketch the curve, sometimes it says eliminate the parameter, and you'll get a new equation with no t's in it whatsoever. Questions? You think we got this? Here's the good news. Your calculator can do parametric equations. It actually has a mode where you put in the parametric equations. So we're going to spend a little time practicing that with our calculator. first one, non.
You can use them in desk too, right?
Yes, except if your answer has a square root of 3, your calculator won't give you that. But you can use it to verify that you're graphing it correctly. Mhm. So go into your mode in your calculator. We're going to talk about some limitations your calculator has too. Your calculator only does what we ask it to do.
Oh, there is a parametric.
There's a parametric there, yes.
I've never even, the only thing I've ever touched in those waiting periods.
Yeah, there's a couple things that you're going to learn this semester that you've never needed
Yeah,
before.
right? That's my secret.
So under your mode button here, it's really small, but I want to come down here where it says function. There's parametric and polar. If you've got a little bit older calculator, it says like para or par. What's the older calculator? What does it say?
R.
PAR. So yeah, same idea. So you're going to go down there and move over and choose PAR. Everyone see that? Mine says parametric, but the older ones say PAR. Now look what happens when you go to y equals where you usually type in an equation. It looks totally different. It actually wants to know what's your x function and what's your y function. It used to just be y equals, right? So we're going to type in, let's do that last one we just did. What was it, t squared plus t? So when you hit, my favorite is this button right here, it has all the variables on it. Usually it's x, but now since we're in parametric, it knows it's a t. So I'll do t squared plus t. And then I'm going to come down here for my y. 2t minus 1? I can't see it from here. Here we go. Now without changing anything else, I'm going to go ahead and graph it and see what happens. So if I hit graph, I only get that. I want to see if everyone gets that or something similar or different. Depending on your calculator and what you used it for, it might give you something else. Why is that all I get? What did it give me? Remember, it's supposed to be this.
Oh, is it because it does the same thing with square roots, right? Because it only gives you the plus value. Is it like
It's kind of like that. It's like something that only gives you positive, but it's not the square root. You're on the right track though.
Because it's counting 5 and 0. there's no
Aha!
such
The
thing as
default in your calculator, so Jose totally saw it. The default in your calculator is to start counting time at 0. It only went from 0 and then up. If we want to, remember we went backwards, we started at negatives. And I even asked you, what if we just started at 0 and I erased it since then? We'd start there and then do just that little
Table
bit.
source is -2.
So depending on how you set your calculator, so I'm going to show you how to change it. Go into your window, on your calculator. I can see window on this calculator. Is that one see window? So it actually starts with T-min and T-max. The default is actually 0 to 2 pi. Because we use parametric so often for things that are trig, 0 and 2 pi. So if we want to match ours, we went back to what, -3? That we went back to? So let's start at -3 for the minimum t. And then our maximum was +3? Or +2, I can't tell. +2 was our maximum? Just to match our table. You guys all see that? I'm just starting here and stopping there to try to match our table. The t step is how often it plots a point. You can adjust this if you want, you don't really have to. If you make it too small though, your calculator will take forever to graph because it's putting so many points in there. So if I tried to change it to something like 0.01, it would take, I don't know how long for it to graph just that little bit because it's doing so many little points. So pretty much I leave that alone. It'll be fine. And this -10 to 10 and -10 to 10 are the same window that you normally have for a default when you're graphing. So I'm going to go ahead and leave those part alone and now hit graph and watch what happens. Now we've got the same graph as before. Did you notice the direction it drew it in? It started down here and drew it here. So it will even tell you the direction if you watch. If you look away and look back, you won't know. But if you watch it graph it, you'll see it go from the lowest point up to the upper point. Yes, sir.
My graph on mine is quite a bit different.
Okay, let's look at your window and see if you have different scale. I'll check that out in 1 second. Questions? Okay, so here's what I want you to do. Play around with this ellipse and the circle just to make sure you can get a good graph on your calculator. After that, we'll take a break, and then we'll come back and talk about how to do some calculus with parametric. Yes? Oh, I get a question. So go ahead and try to graph those, and then we'll take a break in 5 minutes or so, and then we'll come back at 2 o'clock and we'll start 10.2. We have a nice long break. We'll play with our calculators. Before we go on to 10.2, there's a couple other little things I want to say about 10.1. Because when you go to your homework, you're going to say, she didn't talk about this. Well, technically I did, but it's going to look different. So I wanted to point out a couple things. So you might want to get an extra piece of paper out or find a little spot to write on the back of your notes, put a little note somewhere. Because I'm actually giving you 3 more examples. They're small, short, sweet, but find some room to squeeze them in there somewhere. And the first 2 have to do with eliminating the parameter. So when I showed you that one example of eliminating the parameter, what did I do? Just to eliminate the parameter. We solved for t and then plugged it into the other equation. That's what we did. And I pointed to the other one that had sines and cosines that were used in identity. But look at this one right here. What if I want to eliminate the parameter here? I really don't want to solve for t in either of these equations. I could. What would I have to use if I wanted to solve for t?
LM.
Yeah, natural log. I could find the natural log, and I could plug the natural log into the other one. But that's a mess. You could do it, it will work. But you don't have to, this is my whole point. I don't have to solve for it. What I can do is look for something they have in common. Notice that this here is in this equation, and that same thing is in here in this equation. Right, this whole mess, e to the 5t plus 1 is right here, and it's over here. So it's just 7 minus x, right? This is x is that whole mess. So this is real quick and easy. Y equals 7 minus x. I just took what x equaled and that's what is in there, right? We just substituted that whole thing in. So instead of solving for t, you might just solve for something else that you see in common. See, I'm just replacing that whole circle with x, because that's what it equals. Now, there are some restrictions sometimes when you have things like this. E is a positive number. No matter what exponent you raise it to, it'll always be positive. So x will only be a positive number. There's no way you can ever get a negative x out of this. It's impossible. So x will be positive because of this. So we throw that on here. X is going to be greater than 0. Because if I go to graph it, I won't get any negative x's. It's impossible. What is this an equation of? A line, but it's a line only on the right side because the x's have to be positive. See how I knew the x's had to be positive from this restriction here? Sometimes you have those. What about here?
T's, aren't
Oh yeah, they're supposed to be t's. Thank you, I keep doing that. My brain's already on spring break. I told you guys not to let yours go there yet, and mine's there. Change those to t's. 7 to the t, 7 to the 2t.
You can separate 7 to the 2t into 7 to the t times 7 squared.
Yeah, you could actually write this as 7t squared. That's what 7 to the 2t is, right? So what does y equal then?
Y is equal to x squared.
X squared, right? Because that's the x and x squared. So sometimes you're just looking for the same expression in both places as opposed to solving for t. I mean, you could. By the time you do all that, you're getting back here anyhow. So it saves you a little bit of work. There's a couple in the lab that if you do it this way, it's a little bit nicer. Are there any restrictions in this case? Anything that x has to be positive, negative? Can x be anything? Will I get negative x's here? Sebastian's over there going, nope. Same problem, right? You can't raise 7 to a power and get a negative answer. So again, x has to be greater than 0. So it's only the right half of that parabola. By the way, if you graph it on your calculator will know this, and it will show you that you only get stuff on the right. It's important to include that though, because if I ask you to just graph y equals x squared, you guys would draw the whole parabola. But it should be the parabola, but only the right side of it. So you want to make sure you have that included. Questions there? Okay, that's just about eliminating the parameter. The other thing you'll be asked to do is they will show you 2 graphs that relate t and x and t and y. They don't give you equations for them. You don't have the equations, you just have pictures. And then they want you to sketch the curve for x and y. So they want you to sketch the curve for x's and y's. This is hard for some people's brains. If you can't see the relationship, you can always plot points. Always plot points. So for example, if I wanted to make a table plotting points, maybe I put a scale on here. Like that. Scale on the other one too. Like that. Okay. Scale now. If t equals, say, -2, what is my point that I would be at when I find that? Based on these pictures. What's the x that goes with t equals -2? There's a relationship right here. Relationship between t and x.
5.
Yeah, if I go to -2, looks like about 5 to me, right? That point right there, -2, 5. So that's the x value for -2. What's the y value for -2? Can't tell for sure, we're just estimating. -2, I don't know, maybe 6, roughly? Can't tell for sure. My scale is not good. Roughly 6? 1, 2, 3, 4, 5, 6, roughly? We're estimating. So this is one where you don't plug in to find your point. You have to actually look at a graph to find your points. What if we're at -1? -1 to find the x, I'm looking here. To find the y, I'm looking here. So at -1, that looks to be about 1. And at -1 here, roughly 5. Scale is off, I think that's okay. See what we're doing there? When t equals 0, x is 0, and y is 4. Let's do one more. When t equals 1, I get +1 for my x, and I get 3 for my y. So I'm reading them off the graph. Let's plot those points. I'm just plotting the x, y points. So I'm going to start at 5, 6. I'm starting up here at 5, 6. My next point is at 1, 5. My next one is at 0, 4. And then I'm at 1, 3. 1, 2, 3. 4 points. So I have this point, this one got sloppy. This one, and then that one. That's what I had so far. It looks something like that. I went in that direction. What do you think it is? I think it's a parabola too. If you wanted to see if it was really a parabola, if it's looking like one, what would you do? Yeah, maybe more points, maybe another t, see what happens over here. We went up to t equals 1, maybe we go to t equals 2. It looks like we get 5 here, and I don't know, maybe 1, I can't tell. So would I have 5, 1? 5, 1 would be over here. So you can connect the dots. See the parabola a little bit better? You have some on your lab where it's just multiple choice, like matching. And if you're doing that, the table's not the most efficient. So let's say I asked you a true-false question. And I said, without making this table, I just want you to look at these and tell me whether or not this could be true. And then write me a little 3 or 4 sentences explaining why. How can I make sure that this agrees with that? The idea is to look for certain patterns. What are my x's doing here as t increases? As I move left to right, what do x's do? They go down and then they go back up. Right? The x's go down and then back up. So x's, remember, over here, x is going down, they're just going left, and then they're going to go back to the right. So the x's should move this way, and then they should move that way. What did we do with our x's? We moved left, and then we moved right. And we actually moved to where x equals 0, and then went back up. So x's started large, x's went to 0, and x's went back up. Simultaneously, what are my y's doing? Decreasing. My y's are going down. So here I need to go left and then back to the right for my x's. But meanwhile, the whole time I'm doing that, the y's need to be going down. So if I just said I was going to do that all at once without looking, I'm going to start here. I know I'm always moving down, but as I'm moving down, I need to move left and then right again. Right? I move down and I move left and right at the same time. So you can kind of look for those patterns describing how our x is changing, how our y is changing. That'll help you with those matching problems in your lab and on your web design. You can always just pick a couple points too. Like I see it has to go through the point 0, 4. Right? This one goes through the point 0, 4. If you're matching and it doesn't go through 0, 4, you can eliminate it real quick, right? It's not just picking 1 or 2 points works as well. Okay, so now we know about parametric equations. Let's do some calculus with them. Let's do some calculus with them. You like calculus? This technically wasn't calculus. So 10.2. I am on page 95. Calculus with parametric. And before we jump in there, I want to ask you a question. If I were to take the derivative of, I have to get this right. Let's do here. 3x squared plus 7 to the 8. Little review question. How do I find the derivative of this? Chain rule. Right? I have to do the chain rule, where you take the derivative of the outside function times the derivative of the inside function.
6x.
Right, you guys totally know that, right? Well, what is the outside function? If I just want to write the outside function and the inside function. F of, no, F of x. What's the outside function? Just the outside function.
U to the 8.
Something to the 8, like x to the 8, that's my outside function, right? Agreed? And then what's my inside function? Maybe g of x.
3x squared plus 7.
3x squared plus 7. So we took the derivative of this times the derivative of this. Now, we need to put a u in there, you're right. We better change it to a u. We're changing variables on here, I like that. I heard you say u, didn't you say that, Zach?
Yeah.
Because we're finding f of g of x, right? We put g of x in there for you. So when we did, to find the derivative, we took f prime of the outside times the derivative of the inside. Just kind of talking notation on what you're doing when you do the chain rule. Derivative of the outside times the derivative of the inside. Or you could say df du times du dx. Because this is f of u, this is actually equal to u. That works too. When you first learned chain rule, you had all this derived for you and so forth. It helps you explain what we're doing with parametric equations. That's a little review of chain rule. Let's talk about what we do here. To find the derivative is dy dx. So if I wanted the derivative of this particular graph, say, I want dy dx, right? Well, if everything's in terms of t, we have to make sure that we take the derivatives in terms with t's as well. If I wanted dy dt, it'd be similar to a chain rule. Dy dt would be take the derivative of the outside function times the derivative of the inside function. So we would take the derivative of y with respect to x, and then take the derivative of x with respect to t. Because the inside function would have t's in it. For example, if I made this y equals 3t squared plus 7. So the outside function would be like x to the 8. And the inside function would have the t's. Solve this for dy dx though. If I solve this expression for dy dx, what would I have to do?
dy over dt minus dx.
Ooh, not minus, because it's times.
Oh,
You're close
divide.
though. I'd have to divide by this, right? So here's where we're going. This is the formula you're going to want to highlight in your notes. I would have to take dy dt divided by dx dt. This, put a box and a star and highlights, whatever you put in your notes. This is how you find the derivative of a function if it's given to you in parametric equations. You take the derivative with respect to t of the y function divided by the derivative of x with respect to the t function, the x with the t function. And it kind of makes sense, because if you reduce those, the t's will reduce, and you get dy dx. So anytime you're asked to find the derivative, the slope of a tangent line for a parametric, it's dy dt over dx dt. So, let's look at example 1. Example 1 says find the tangent line or lines. Key point here, you might have more than one tangent line, which is hard to imagine, but I will show you why. Line or lines. Find the tangent lines. Tangent lines. We don't know if it's plural or not yet. We'll talk about how to find that. To the curve defined by this mass. 4t cubed. Y equals t squared. At the point 0,4. So this is technically like a Calc 1 review question. Find the equation of a tangent line at this point. Right? We did that. You did that in Calc 1. So what do you need to find the equation of a tangent line? Grades can't go on spring break yet. Hang on to them. Equation of a tangent line.
Where the slope is 0?
Well, the slope doesn't have to be 0. Okay, let's look back up. Let's go to algebra. What do you need to get an equation of a line?
Cumulative slope.
You need a slope.
2 points.
You need an m, or 2 points. That'll give you a slope. So you need m, which you could get from 2 points. And then you just need one other point to write the equation of a line. So you need a slope and one other point. If you have 2 points, you can get the m. But when we're talking about tangent lines, what is the slope of the tangent line?
It's like a derivative of function.
It's the derivative of the function. The derivative is the slope of the tangent line. If you guys had been in my class for Calc 1, I would have had you repeat this out loud, I don't know how many times. The derivative is the slope of the tangent line. It's also a rate of change. It's also, all these other things it's all equal to. So I need the derivative to get the slope. So if I want the derivative, I need to take the derivative of this function. I need dy dx. The slope is the derivative of the function. Okay, so we just came up with that equation over there on how to find the derivative. What am I going to do? Derivative of y with respect to t divided by the derivative of x with respect to t. So the derivative of y is 2t. Derivative of x, 5t to the fourth minus 12t squared, he says. And I need to evaluate this at t equals, I have no idea. Back in Calc 1, you evaluated your derivative at x. You plugged in your x value, right? And then we know what the slope is there. But I don't know that x equals 0 is the same as t equals 0. I have to plug t in here. Question is, what t do I plug in there?
Would you plug in the 0 for the x and y, and that's what you,
Not the x and the y.
or just the x?
So the 0 is the x and the 4 is the y?
That's what I meant.
That's what you meant? Okay.
Like respectively. like
All right.
x and
So we need to know what is t when I go through that point. So you know how over here we made tables, like in this particular one, t was 0 when I went through 0, 4. If I want to know when I go through 5, 6, t had to be -2. But the question is, what t will get me there? So before I can finish this, I need x equals 0 and y equals 4. I need both of that to be true at this point. I need to find t that makes that happen. Find t. So if x equals 0, I'm just going to set that equal to 0. 0 equals t to the 5th minus 4t cubed. And I need 4 equal to t squared. Now I have to solve both of these. The whole goal is I'm trying to find the t that puts me through that point. So how do I solve this one?
you're gonna take out a piece of cube.
Yeah, factor out the t cubed. I get t cubed. I'm left with t squared minus 4. So that's t plus 2 and t minus 2. So my values for t here are 0, 2, and -2. That tells me that 3 different times my x value will be 0. It goes through 0, x equals 0 at 0, at 2, and a -2. If I solve this one, what do I get?
T is equal
I couldn't hear you, Joseph.
to t is equal to plus or
2
minus
plus or minus 2? Okay. So I only go through 4 at those 2 values of t. So let me ask you this question carefully. Which t values will put me through this point? Which values of t will put me at the point 0, 4? Yeah, Joseph?
Because you're -2 and 2.
Just the -2 and 2, not the 0? Why not?
Because it doesn't go through 0 and 2. It doesn't
Uh-huh.
go through 4 and 0.
So 0 will give me x equals 0, but 0 doesn't give me y equals 4. So this does not help, this is an extra guy, we don't care about him. That's why I underline the and here. I need this to be true and that to be true. So it's only gonna happen at 2 and -2. So that tells me that 2 different times I go through that point, which means I'm actually gonna have 2 different tangent lines. So I need to evaluate this at t equals 2 for one line. And then again, which I'll do on the other board, for t equals -2 for the other line. And a lot of people don't understand why there's 2 tangent lines. Let me give you a visual. I don't know if this is the exact graph. Let me give you a visual of why there'd be 2 tangent lines. Let's say my parametric curve looked something like this. My parametric curve looks something like this. This might be the same curve that we're looking at. And say this is the point right here. Where are the tangent lines at that point? What do I mean by a tangent line? Yeah, it touches there, but it does more than touches there. What does a tangent line do with the curve? I mean, because I could draw like a line here, that's not a tangent line, right?
Tangent line is,
What's it do?
It touches the curve at one point and gives the slope at that exact point.
Yeah, it touches the curve and gives the slope. I like to think of it as it points in the direction the curve is moving at that point. So at this point, it touches there and is tangent there. So like one tangent line would be, erasing as I draw it, would be like right here. As I go through that point the first time, my graph is pointing in that direction. So there's one tangent line. But then I'm gonna curve around, and then when I get over here, I'm going through that point again. Now my tangent line is doing this. The same point, but at different times I have different tangent lines. Maybe at -2 I was on this one, and I loop back around at +2 I'm on that one. See how there could be 2 different ones at the same point? It's different than functions for sure. Okay, so now that we have that, let's find them. So this is the slope for any point. We decided it happens at 2 and -2, so I'm going to evaluate at +2 first. I'm just going to plug 2 in there. Plug 2 in for my t. That's 4 over 80 minus, what's that, 48? 4 over 32? 1/8. So what is that 1/8? The slope of the tangent line when t equals 2. I need the equation of the tangent line. How do I get that?
y1 equals m times x minus x1.
This works for any point? Any point, any slope? Y minus 4 equals my 1/8 times x minus 0. Just plugging in my point and my slope that we just found. 1/8 x plus 4. That's one of the tangent lines. This is the tangent line when t equals 2. You don't actually have to designate this. If I just say find the 2 tangent lines, you find the 2 tangent lines. This is the one when t equals 2. What do I need to do now? Yeah, do the same thing at -2. So the slope of the other one is dy dx evaluated at t equals -2. So I'm just plugging -2 into my slope formula. 2 times -2 5 times negative 2 to the 4 minus 12 times negative 2 squared. Run that around. Ends up being negative 1/8. So now I do the equation of that line. Y minus 4 equals negative 1/8 times x minus 0. And you get negative 1/8 x plus 4. So they're two different tangent lines. What's going on there? Questions? And hearing heavy sighs.
Question.
Yes.
So on the last summit we submitted, would we, you just squared off that, would you want us to write it when t is equal to 2 and t is equal to?
No, so that's what I said. I wrote it here just so you knew that that came from that one. And same thing here. You don't have to write this part.
As long as we have both, you'll.
Yes. I'll be able to follow that you have both. It helps just to organize, because like if you're looking at your notes later, you're like, where'd that come from, and where'd the other one, and there's two different ones. So there was an easier way to actually do this. There isn't always though, which is why I showed you the harder way. The easier way is when you eliminate the parameter and just have a function with x's and y's and do it like you did back in Calc 1. So if I wanted to do this problem one more time, quicker, I could eliminate the parameter and then find the equation of the tangent line. You actually have a lab assignment question that asks you to do exactly that. Find the equation of the tangent line by eliminating the parameter and by using parametric equations. So I'm going to come over here. Same problem, see if you can find some room on there somewhere. Now eliminate the parameter first. And then find the equation of the tangent line. So if I want to eliminate the parameter, these are my original equations here. Eliminating the parameter got a little bit tricky. Can you solve for t in either one of those? Yeah? That says, yeah, which one you want to solve for t in?
Square root of y is equal
Yeah, this one, square root of plus or minus square root of y would equal t. Right, we solve this one. So if we use the second equation, we technically need the plus and the minus square root of y equals t. Two different ones, right? So let's use the positive one first. And then we'll worry about the negative one, which I'll probably not even do because you guys are gonna say I get it, so. So let's use t equals square root of y. If t equals square root of y, what am I gonna do with that to eliminate the parameter?
Put it with the next equation.
Yeah, put it in the next equation. Replace all of my t's over there with square roots of y. I'm gonna write it right underneath here. You can't see it. What is it? T cubed, t to the fifth minus 4t cubed? Is that right? Yeah. So I'm gonna put that t in here. X equals square root of y to the fifth minus 4 times square root of y cubed. Looks ugly, I agree. Just change it to a fractional exponent, it'll be prettier. Y to the 5 halves, if I could add. Minus 4y to the 3 halves. Right, because the 1/2 is the square root. So this now, I've eliminated the parameter. I have x as a function of y. So then I need to take the derivative. I take the derivative so that I can find the equation of the tangent line. Now be careful, since I have x here, it's going to be dx dy, right? Not dy dx, it's dx dy. You could do chain rule, and you could do implicit, I suppose, to solve for dy dx, but this will work just as well. So the derivative of x is just dx dy. What's the derivative over here?
5/2 times y to the 3/2.
Just bringing down, using the power rule, bring it down, subtract 1, minus, that'll be 6, 3/2 times 4, y to the 1/2. And I'm evaluating it where? At what value?
0, 4.
At 0, 4, do I need x or y? I need y, right? So I need to evaluate that at y equals 4, because I'm at the point 0, 4. And if y is my variable, I'm going to plug in that 4. Five halves times 4 to the 3/2 minus 6 times 4 to the 1/2. We talked about these before. It looks scarier than it is. This says take the square root and then cube it. Square root of 4, 2 cubed is 8. So this is 5/2 times 8 minus 6 times square root of 4, which is 2. So I have 20 minus 12. Add a room here. That's 8. What is 8? 8 is, in words, what did I just find?
dx dy.
Yeah, I found dx dy. Dx dy equals 8.
So that means slope is
So what if I want dy dx?
Invert it.
Inverted, right? 1 over 8. Which is our slope. Which we could then do the exact same equation here. Our slope is 8. Equation of the tangent line would be the same. And then if we really wanted to torture ourselves, we could do it again with the negative root y. Guess what's going to be? Negative 1/8. And you never know if eliminating a parameter is going to be quicker or faster than doing it parametrically. Sometimes it's worth a try. Usually I decide by how easy is it to solve for a t. If I could easily solve for t, I might eliminate first. But if not, I have to leave it there. Question set. Okay, I'm going to leave that last example for next time. So we'll do example 2 next time, and then we'll cover section 10.3 as well. Make sure you're ready to do some trig by Thursday. It's all over the place. You guys looking good.